the right hand side, which basically produces this interaction between aerodynamics and structural stuff. Structural stuff, including all this coefficients and quantum matrices here, they all produce this kind of reaction. So they react to the interaction with the forcing, which is induced by the interaction of the structure with the flow. And that could be both lifts and a moment, a dynamic moment. If you have only plunging 1 degree of freedom, there will be one equation. This one equation will only contain the plunging response with the lift. If we have 1 degree of pitching, there will be one equation with the moment. Moment will be the responsible thing. Right? So this will be basically a coupled system, which is responsible for the aeroelastic response. And that's what basically responsible for crashing the wings. That's what basically what Theodorson came in the 40s and explained the entire phenomenon, how he solved the system analytically, and he predicted everything based on anesthetic aerodynamics. So the idea for us is actually to have this new geometry, because again, if you have this kind of geometry like here, NACA 0 12 or something like that, 0 10, and that's what the experiments were done for the flutter, which were validated against. So our original model was validated against experiments, which was done, of course, for the regular NACA 010 airfoil in Germany, Sweden, Royal Institute of Technology in Sweden, Stockholm, and they did a very careful analysis for this, what they call LTO. So LCO is a limit cycle oscillations, which is a limited form of flutter. Flutter is exponential growth. So flutter, you just grow exponentially until it's like you destroy it. LCO, you have the nonlinear coefficients, which actually like damping coefficients. It's damping coefficients when they are linear, which is basically assigned to this system for springs. All of a sudden, you can actually suppress this infinite growth, but you go to the limit oscillation. So you oscillate with some constant amplitude for the plunging or constant angle of attack. So you don't go exponentially, but you oscillate with the same amplitude. And that's called limit cycle oscillations. So we usually investigate LCO. That's what we're working on. We don't want to have flutter. If you have flutter, pure flutter, the system will not work because of the story right away. So you should be careful now for these things. So this is LCO. You see it goes up and down with more or less the same amplitude. But this is actually uncontrolled right now. Because you see it kind of goes like, oh, then it's very hesitant to go. Now, the idea that you put there, this is no SGA, no synthetic jet actuator. So if you put your synthetic jet actuator for this particular design, here and there, you can control aerodynamic moment. You can control aerodynamic moment, you can sustain the moment that you want, and by this, through the coupling between the plunging and pitching, you can sustain the plunge. So you just need a little bit of moment, not much, to be able to sustain the plunging motion. That's what we extract the energy from plunging. So if you do this in sync with this natural shedding, which is coming from the plunge or pitch, right? But it depends. If you have pitch, which produces natural, frequencies, and you have plunge, which produces natural frequency, which is all different. But they actually combine in a real flutter. But in the process when it's like before flutter or induced flutter, it's actually not combined. So it's a bit of a theory, but that's it. So anyway, so we can control this whole motion and make it sustain. And that's the whole thing which we try to investigate. So this is actually flutter. So that's our original research we were doing. You see, when you start doing the situation, boom, all of a sudden you change completely the system of vortices, which I shared. This is the wing with the installed this all array of synthetic jets right there. You can see like on the side here. That's how it looks like an experiment with Technion run. That was an experiment done in Israel. And you can see that they did this whole experiment. But originally, our design was actually to suppress flutter altogether. That's how we did it, because that's the classical problem. Classical problem is flutter suppression. That's what people try to do for so many years. And that's how it comes out. So you can see, all of a sudden, this is limit cycle oscillation. So this is angle of attack. So it goes to the same angle of attack. That's LCO, pitching LCO. And all of a sudden, you have this synthetic jet, and boom, you reduce this LCO to zero, almost zero, basically suppressed. That's it. That's the thing. So we put this all together in the linear control system. That's what we again our collaboration with the physics guys could do this nonlinear controller. There's a lot of maths there, but basically you could put it together and you have this automatic control, nonlinear closed loop control system, feedback loop. And that's all part of the. You have to have sensor, and you have to have actuator. And this is a combination between the sensor and actuator. You have this closed loop. So you get information about, for instance, the amplitude that gives you information on how much actuation you need to apply. And that's what the sleeve, which can be sustained. So this is the project which was sponsored by NSF, self-sustaining with energy extraction technique. We call it SWEET. They really like those short notations. So it's CSWET, SWEET, using multi-level control design. That is, if you don't have these things, you don't get a grant. So you need to come up with a very nice variation for the project. So they're like, it's all psychology, people who check this stuff and the reviewers, it's all different stuff. Anyways. So again, this is the code which we're using. Again, part of the collaboration with the Air Force Research Lab for many, many years. We did a lot of development together with them. It's good. I'll talk about these developments in different parts, different talks, because will be different projects and in many projects we use this code. So I'll talk about this later on. But it's basically solving the strong conservative form translated compressor in these talks. This is a form. Again, for those of you who did CFD, you understand what it is. For those who don't, that's a problem. But this is Navier-Stokes equations in conservative form. With its Q as a solution vector, and then we have the energy, pressure, 6 order in space, accurate, second order in time, scalable, efficient, huge legacies, hidden publications. I don't know how many, if you count, maybe hundreds. Literally, it was like very much validated against students with benchmarks. It was experimentally and analytically, and it was not just for this toxicity. Us, we were doing elastic analysis, noise analysis. In reality, everything what Air Force was doing primarily is aerodynamics, unsteady aerodynamics, flow control, aero-optics. By the way, it's very interesting field, aero-optics. There's a lot of things with this as well, and so many other things. So that's a very common problem. So very briefly, because again, I'll talk about this in detail. There will be separate presentation. I don't know. It's going to be like different levels of detail. So LCO. So this is LCO cases for us. It's all about what we call numerical experiments. So we do numerical experiments with different things. So for instance, this is the natural frequency of pitching, 4.5 hertz for that particular design. This is natural frequency of plunging, amplitude about 0.2 chords. The LCO given pitching uncoupled. That's what I'm saying. Before it gets flutter, real flutter, it's uncoupled. Two frequencies control. And then you can control things. You have 2 degrees of freedom, so you control both plunge and pitch. Or you can fix one, just do the plunge. Or you can do closed loop or open loop. You see, there's variety of different test cases you go up. That's all experiments, right? Yeah. And the idea is actually you can basically control in sync with this frequency or this frequency, and see what direction will be. You either control like trying to pitch. Trying to plunge, but in the end, you want to look at the plunge, right? Your bottom line is the high plunging amplitude. That's what you want to get. Because that's how you extract your energy. More amplitude, the higher the energy you can extract. And frequency. Well, frequency again. For that in case. So these are the CP results. You can see that pressure coefficient on the whole 0 angle attack, 0 like this. And then you have upper lower surface, and you can see how things change between the actuation and no change. No SG, upper surface SG. And you can see, of course, if you have no actuation, it's a symmetric airfoil, no angle attack. What happens? Everything should be like aligned, right? On both sides, should be the same pressure coefficient because it's all symmetric with no bias. If you have actuation, all of a sudden you have this change. And this change in pressure, that's the one which produces the moment. See, that's the whole sequence of steps here. Of course, everything is pretty chaotic in terms of the overall, like heat coefficient goes all over the place. There's a lot of shading frequencies there, et cetera, et cetera. So it's not like a state line in reality. Of course, everything gets averaged in the end. But in reality, in real life, everything is like all over the place, right? The average is what you're looking for. Like, for instance, from the lift, this is the average. When you actuate, this is the average. So you see the bias. And that's the effect. Of course, that's what you would record eventually. The difference in lift will be because of the different lines here on the average. The same for the moment. Boom, boom. So for the lift, you could probably create some sort of bias if you have symmetric knock airflow, but there will be no moment. You cannot create moment. So that was the whole point of this patterns. This airfoil and G airfoil we design this particular one because it creates the moment vibes, and that's what we need to be able to sustain the fun. That's the. So again, some experiments. I'm going to look about it more. You'll see that this is how LEAP develops. Protect the plunge and pitch. Let's see how control 2 degrees of freedom, control, closed loop, open loop 2 degrees of freedom, plunge frequency effect. And you can see it's all over the place. And usually that's what you would see. The reaction is different if it's uncontrolled. With the control, you have more reaction, but the average of this kind of different. So that was the preliminary, good success. So you can see you want to have it stable, right? You have the same amplitudes. That's what allows you to sustain. So 2 degrees of freedom, open loop, plunge frequency effect was promising. But in the end, this is the winner. Of all the winners, of all the different cases, that was the winner. This is a 1 degree of freedom closed loop plunging control in sync with the plunging frequency. So that's where we get the best response. Sustainable, robust, and you can actually get the energy piece. So that was the thing. Closed loop control shows potential energy extraction on a wide range of also wind speeds, because we want to make it as it works. It can be used for people in a household. So you put it in the air, it can rotate towards the wind. And every time it will be moving and it's getting energy, and here you go. You don't need, if you have no sun, no solar panels, at least you have wind. Yeah.
We have a question. What is the energy potential of this type of technology?
So yeah, that was calculated and put in the actual numbers. But you can put the pretty good things for the household. Its household has specific needs. Usually in the advertisement, people put some numbers there. Okay, that's how much you need and how much this. But it depends on the sizing as well.
Yeah, I was going into that.
Yeah, it's all sizing. How big is the size?
Yeah.
Well, let's say it's a meter by meter or something like that, or 2 meters by 2 meters. It depends.
For example, if I wanted to produce a kilowatt power.
Yeah, so that was calculated on the regular. But that can be done, but also, you see, there's a potential for those things to develop. It's not just a single plate, it will be cascade. It will be cascaded plates, and then you can actually have what we call tandems of cascade. Because in fact, we were showing that the tandem section would work even better. You have the other one will react to this guy, so there's another vortex, so there's some interesting thing.
But one behind the other.
Yeah, not only in this thing, but also another one thing. So it will be like tandems of the cascades. Cascade tandem. Not just single plate, cascade tandem. That's, you see, you have different options. I mean, you're the designer. So that's all up to the guy who do the experiments. You can do numerical experiments and see which one would be the best. So that's a lot of opportunity. That's why we do numerics. You don't have to build the whole thing every time. You just do the experiments numerically once you validate your modeling process. You can do that. But yes, those numbers are in the proposals. Because that's why we put in proposal. Here we go. I mean, we can supply the whole thing for the entire. It was working well. I don't remember exactly. But again, it all depends. We didn't do that's all preliminary because we only did for single plate. If you do again multiple plates, if you do the tandems, it will be different. So that was up to the next stage of this STTR proposal for the business development. Right? So it's a potential for us to collaborate on these things, of course. Yeah, because in the end it was development of the reduced order model. Because all this high fidelity stuff is very expensive. You can run the case maybe days or weeks, depends. But the reduced order model usually develops some kind of analysis, which is basically will be more sophisticated like panel methods. And with this, you can actually get much faster, very fast. So you can do design optimization. All right, so that's another project, dynamic soaring. You can go to separate presentation. We'll see. I mean, I have to go into this. Maybe a lot of things will be repeated in the end. In the other presentations, when think about what's separate class. But this is actually very interesting project. It has a whole legacy. So in the last one, I actually have already 80 slides for the actual big presentation because there's a whole big legacy of this project. Started maybe 10 years ago, honestly. In the original design, original idea, but actually at that time we had Dr. Goodmanson with us. You know Dr. Goodmanson? So that's another Bible writer. I call it Bible right now. So we had the Bible on helicopters for Leishman. There's a Bible on general aircraft aerodynamics. That's Nori Goodman's son. He actually has second edition, Ryan. It's really big. That's why they're really big. That's why they call Bible. They're really big. And that one is all about aerodynamics of like general aircraft, like small aircraft. Because he worked in a company, I forgot, it's not Cessna, it's another one similar. Not the name, but anyway, there was some company, one of those like Beechcraft, that's different, which designed those aircraft for like public use, right? Private use. Actually, he was the best designer ever when he came to us, and I was his PhD. That's funny because he didn't have a PhD degree. He would come, and he would have to get PhD degree to become a professor. So I was his advisor for PhD. He is like a world expert in aerodynamics. I was his PhD advisor. Still, anyways. So he got his PhD degree and then he left. He was with us for several years doing design, and then some startup company which developed some aircraft. I don't know which one, but I think he kept it as a secret. I guess I don't know which one. So so he became like chief aerodynamicist and stuff. I guess they offered him $1 million or something salary. So that's he said okay, bye bye. So we have another guy now doing design courses, but he was the one. And so he was very interested as well. Together, okay, he was doing a lot of biomimetic flights, like bio things. So he was thinking about albatross flight for a while. That's why we started this one. It's all about albatross. Yeah. So if you have this wind shear, these guys can extract energy. As I mentioned before, it's basically the cycle, which we call 4 stages: low altitude turn, windward climb, high altitude turn, and windward descent. So like, that's how we fly. That's how albatross flies. And then the so-called the Arctic, something like that. Correct. In the end, it's a method of yeah, that's well, this is a plate, don't flat. I saw them actually. There's at New Zealand because they have a huge harvesting breeding spot there. In New Zealand, there's some area where there's whole natural park full of albatross, and you can see those huge birds. Huge. I think it's one of. I think it's biggest actually. It's the biggest bird. The second after turned up. But we don't have those. But it's like the biggest bird, and it actually doesn't have to fly. You know, the smaller the bird. By the way, if you teach if you take aerodynamics class, if you do like low speed aerodynamics, low resonance number aerodynamics, you'll explain to you why the smaller the bird, the harder it should fly. You know, because the tiny bird always flaps, the big one doesn't have to, and that's actually very interesting. Maybe I have some slides somewhere like to explain this wise, but it's all about this huge drag difference in some particular resonance range. All of a sudden you have completely different like drag profile, and so all of a sudden you need to really work hard to sustain your flight for small resonance number, and that's actually. So this guy doesn't have to. It's huge bird, so it can fly like an aircraft. Don't have to fly much. Anyways, so. Involves gliding, also motions, but to achieve dynamic soaring by continuous recurrent flight. And that's basically this maneuver. The bird airspeed increases with wind speed to maximum speed of 20 miles meters per second. So a lot of research was done originally to explain the physics of this biology of this thing, fluid mechanics of dynamic soaring. So they published there, but it was actually legacy goes back, as I mentioned, to Lord Rayleigh in the 19th century. He was actually watching this closely, figuring how the heck they can do this thing. So he was able to sort of explain ideas, not so much details. Details was actually, I think in the 60s, there was a guy, I'll mention that in my separate presentation. He was actually doing a lot of investigation. That is actually came late. But before that, there was a guy in the 60s or 70s who was really getting into the physics, trying to explain this. Anyways, for us, again, details will be left for the separate presentation in this published. But the idea was to design the autopilot with this controller based on reinforcement learning. That's the first time we tried to use artificial intelligence in aerospace. It's funny because several years ago when we talked in a group meeting and Dr. McBarry, and so there was a question, everyone talks about, AI everywhere. I mean, should be like try to use it in aerospace. And he was like very skeptical. How it's going to work. I'm not in aerospace. and then we started this project to see how it's going to work. And that's our best chance. Of course, you can do a lot of data training now, a lot of things like this. A lot of CFD is now using this, data training analysis. So it's like machine learning and stuff like that. So reinforcement learning, of course, is part of machine learning, which is part of artificial intelligence. All of it. So that's the thing. And the key elements of this thing in the process, how we're going to control the motion, doing dynamic sovereign, learning process. It's all about the interaction between agent and critic. So there's you probably know something because it's actually part of the MATLAB now. It's a lot of things which is done here is MATLAB simulator. So in MATLAB, they have the actual algorithm which you can try it, see how it works for different things. But in the end, it's different map states and it looks at the action, deterministic, stochastic, parametric, involves neural networks. And there's different algorithms which we tried. The best which we found was called deterministic policy gradient, DPG, which seems to be working best. And so it involves agent, environment, action, critic. Critic develops the idea how good is your action, and they produces a reward function. And in the end, by the way, reward function was the key for us to get success. Apparently, the reward function is very, very tricky. And by the way, that's pretty much like how the child or anyone else starts working or doing something, right? Or bird starts flying. It's all about the learning process. So if you work fine, they give you a candy. Right? So it's basically a reward. So that's how you don't want to work, because they give you like some sort of reward for your good actions. So that's life. That's how things work in life, and pretty much that's all implemented as part of this algorithms. It's kind of reward for your good action. So if you develop something that works fine, or you try to fly this thing and get the energy from, you'll get candy. So that's the idea. Or you learn these things. Right? So all these elements are part of the system. So policy might be generated to balance exploration and exploitation problem. So all these things deliver the word action. It involves neural networks, so that people layers, inputs and outputs. So acting critic again are critical. Most critical because that's actually become the sort of the collaboration between them to implement the proper process of this thing. But it goes through a lot of steps there. And that's what they usually start building all these diagrams. That controls the action sent to the glider. So the critic has statements made of the action made by the actor and so on. So actor critic, neural networks policy optimized so they sell. So, but this is not so simple. If you want to develop some algorithm like this, you need to predict how the aircraft will behave. Right? At each step, like when you go to this kind of maneuver, you go to very high angles of attack. Doing the roll, doing the plunge, doing everything beach. So side sleep, all these elements here, usually they range from minus 40 to 40. Side sleep, minus 40 to 40. Of course, it's not just your panel method, because there's a lot of separation going on, a lot of stuff. So you have to predict all these coefficients, like control aerodynamic coefficients, right? For CD, CY, CL, CRO, CM, all these things, 6 degree of freedom system for the aircraft flight. So that all involves lookup tables, which will be part of this whole system. But lookup tables will involve solutions from CFD. Because again, panel methods can only work so much. But if you go to variables, you cannot work. So we did this analysis. It's a RANS. So again, the RANS, we Reynolds average non stokes. Reynolds was about 300 small cases maintained for people operation. So it's also about sizing, right? So we have the size, the aircraft we showed for UAV, it's like mid-size, like something like this. And albatross, right? So pretty much trying to match this. Scale, maybe that's just getting turbulence model. Point wise was used, that's probably used with here. So in this particular case was actually ANSYS. Most of the simulation here was done using Fluent, which is ANSYS. So because OpenFOAM is a bit more sophisticated, we actually have to spend a lot of time to know that's a bit of a steep curve. And those guys, that was primarily a supplementary tool for them get those coefficients, but most of the stuff that we're doing, like all this controls, all this people intelligence stuff. Validation was done against wind tunnel, but they did run wind tunnel. That was, as I mentioned, this project involved several students, several, not the generation, but several students. That's the enormous, several generations including too much. So, for instance, the Gladstone Joseph, his guy came to me around 2016, 17-ish, and then he continued with that. The other guy continued, and then eventually this project was, pretty much completed about 1 year ago or 2 years ago. We still have to publish the paper. A lot of things was done by Jacob Adamski. That's my student who defended his thesis. Both of them defended the paper. Jacob was the one who actually finished with RL development, Air Force Mundial thing. And then finally, the guy from Korea, he left recently. Yeah.
Quick question. When you report that range of number, what is the surface of the reporting area?
We're matching the glider which we have, but the make glider is actually trying to match albatross typically. So that's just 1 meter. I forgot the numbers again. Oh, maybe the numbers here. So. Wing area, in metric. Yeah.
Don't see
Chord lengths, 42, altitude. Yeah, it's all metric. That's very much the numbers.
the range of 6 in terms of the code.
Yeah. It's you. This is kind of CPU what you were doing, different conditions for the boundary, pressure output, humidity, etc. All these different characteristics. That's how it was matched. The whole aircraft was matched, so it's all here. And we would just go to some sort of conditions when it goes to slide, very high, beach, etc. So that's a typical thing. And that all was feeding into the MATLAB simulating model, which is 6-degree feeding closed loop non-linear aircraft simulation. So these folks are aerobatic glider, so that's how it looks like. That's the one which is still sitting in my storage, waiting for the guys to continue to finally fly it on this project. Because everyone is left now for this project. We have other guys who had to put everyone on the NASA project because it was a big emergency. But anyways, we still have to finish with the real flight. Everything was developed. So components you can see here are dynamic coefficient lookup table to the fourth moment. Then with shear, propeller thrust, joystick input, total animation, and the training model, which is part of this thing. So it's all like put in here. And the bottom line. So again, I'm not going to talk much about this project to go to second. But this, let's look at that. So what we want to sustain in the same altitude during the flight, right? Or we look at this energy in terms of energy, how much you sustain the energy for the flight instead of losing. So we got to the point when the total energy could see the rate of total energy was actually sustained, but we still were losing energy, and by this we're also losing up. So that was preliminary stage of our design that we actually got a lot of things. We got it not like as if it's dropping right away, but it's actually still losing energy, right? And it took a lot of effort, about 2 years of work by my student, which is just recently finished Korean guy. So he actually was able, he didn't put the right colors, but he was able to sustain everything. And then everything was done through the optimization of the reward function. That's why most of the input was. He got the reward function properly so he could finally sustain the altitude and not lose the energy. So apparently that depends on the amount and size of your kit. That's a lot of work. So if the kitten is good enough, then it will fly forever. So that's probably philosophy. Yeah.
One question. So you have to define like your surface, your control surfaces, and based on that function, then apply the right amount like of motion to each.
Yes. Yes. It's basically all coupled together. It's all running the system. And it goes through a lot of elements. There's sealants of it. Again, I'll show you later on next time when I will do this. It's a lot of things. I mean, these guys did a lot of work. And both him and there was several people involved. Yeah. The thing about we got the award from, as I mentioned before, we got an internal award from university called Ignite. So this that's why it's showing the log of this. It was presenting to the university later. So the idea was that the university will give an award to the student team if it's really exciting, something really big. And we'll told them that we're going to fly this together with albatrosses around the circle, like Arctic Circle, with the logo Embry-Riddle, like the whole plane. And they said, that's the best commercial ever. That will be on all CNNs. And the university will have like twice in Rome. We already got too much. Like, actually, we don't need too much students already. I mean, we have too much, like 2,400. So I'm just scared to come back. When you teach the classes like this big, you don't remember anyone. And we now don't have enough faculty, even though that would awesome. All right. So, as I mentioned, we're starting to get into the smart materials things. That's actually new. In fact, both the student Alia, that's she's from Kazakhstan, she's both in smart materials and she's doing experiments. She did experiments. Both of those things are new to me. But we started collaboration with some other faculty. She's experimentalist, so she was helping on the way. And we had some materials guys who were part of the team as well, like Professor Damon, his materials guy. So that was part of this. It's all about what's called wing body junction flow. So if you look at this is a fuselage of the aircraft, it's the wing, and then in the junction between those things, you have the junction vortex. So this junction vortex creates a lot of problems. It creates a lot of drag, reduces the efficiency, all these things. So people try to fight it for 20 years. Now you'll see again, there's ways to do that. If you look at the Boeings or Airbuses, did you see that inserts? If you look at the here, this is your right there. See, this is your wings. This is your fuselage of Boeing. Or no, it's A38, Airbus 3. What they call it, they have this wing root fairing. They call it wing root fairing. Yeah. So they try to smooth the transition from fuselage to the wing to reduce the size and the strength of this works, of this junction works. It's limited success. I mean, it's like those things they put on the winglets, right? So you have the winglets, right? So of course you can reduce to a limited degree your induced drag. That's what they for. They try to reduce induced drag, but of course you still have a lot. So we try to do something which is kind of nobody tried. We try to move this thing. So the idea behind this project is to have some smart material which will be actually oscillating with some specific frequency, trying to control the impact on this full works, trying to see how this will react. It's a pure experiment. Nobody tried. We started this, and then we can do CFD later. That's what she's doing right now. She's actually learning open form, so she can do that. So she finished the first part, very preliminary, first year master's thesis now, she's doing PhD. That was to look at the experiment. So she had materials, that's where we got those materials. So that's the full characteristics for respiration gradients, given streamline, liquid presence, secondary flow, streaming. So a lot of physics that involve with produce this thing. Do you understand? There's a vortex which is produced. Bottom line is that you produce drag. We were seeing, and it's very 3D, complex, and predictable. Yeah, it's a lot of things. In fact, by the way, we have another guy who's trying to investigate with we call him Professor G because that's he's from India, from actually Chennai. People from Chennai has last name with many letters, so we just call him Dr. G. It becomes impossible. Anyways, so he's actually in charge of the wind tunnel right now since Richmond left, Gordon Richmond. So he's in charge. He's doing an experiment with his student Paul. We thought we would collaborate much with Paul, but Paul is now at university. He just got married, so unfortunately we don't see him much. So Paul, just do invite yourself. So we'll help you as much as you can, as we can. Anyways, so this is a conventional solution again. This kind of little fairing fillets, smaller junction, static fairing suppress small separation, increasing for drag ratio improve. That's the bottom line. That's what we're going to do. Improve our dynamic performance. Mitigated with suppression gradient by adding flow around the junction. Too large fairing, but of course they add weight. They limit success in friction drag. So the idea was to design some sort of material which would be lightweight, and it's, it can isolate and do everything. So that's what we came with the need adaptive solution that can provide effective flow control across multiple flight regimes without incurring constant drag pattern. So this is a recent article we published in Journal Actuators. She was basically looking at all possible designs which are available right now, including this PAM, pneumatic artificial muscle. Pneumatic artificial muscle stands for PAM, and that's basically this design which she's trying to move. And it's published very recently. It's all of you. In fact, for that reason, you get emails like, we invite you to do this, now go to the conference. So now I'm getting students every day just because I have this biology thing. And I'm just a killer because they now invite me to all kind of medical conferences. Like, I'm not a medical doctor, but now I'm like as an expert in the medical field. Like, yeah, I'm not, anyway, so they want to present everywhere. Not to talk about just aerodynamics. I mean, of course, our acoustics aerodynamics is originally was the field of propulsion, but this is now a new field. This PAM, because everything particularly important for in PAM thing is robotics. It's all robotics. So this exoskeletons, exoskeletons, those things like I guess Trump's dream. If you sit inside, become like a huge robot and can control it and crush everyone. It's like they like to show this in the movies, right? Like Terminator. Something like that. So this is actually the kind of device which related to this kind of PAM stuff. So now, anyways, so this is actually what she started to do. It's what's called McKibben actuator. So this is something which can actually, depending on voltage, for instance, it can change its length, it can change vibration, it can change a lot of things. And she was doing this deformation characterization pretty much with this expansion on McKibben actuator, because that's what she was going to put in the insert in this big farm program for the junction. So a lot of experiments she was doing. That's what this junction is right there. This thing is now, see, it's moving a little bit. Yeah, so it's moving with a low frequency, but you can increase the frequency, and most importantly, as part of the research, the idea is to see which is the most sensitive reaction, which frequency is the most interesting for the most important input, most critical input on the works development. So that's she was doing different amplitudes of different frequencies, just experiments, information on the form, and she was doing this. Kind of a triggering kind of things, different cross the range of angle of attack, cross the range of frequencies. Eventually they should be moving. It's moving, it should be moving. Oh yeah, go. So there's a movie which you actually record the lead, but with this thing of moving, how this vortex is generated, etc. Again, a lot of preliminary study. That's a different. This is 0 hertz. This is okay. That's not actuation. This is actuation with 10 hertz. So that she could look at the differences experimentally. Not much she was doing quantitatively, because that was the small wind tunnel which didn't have much things there. Because for the large wind tunnel you have to pay by them. So they developed this huge facility with a pretty hefty payments for each hour you run, even for faculty. So if you bring your money from the grant, then okay. But if you don't, sorry, go to the small one. You cannot do it. So yeah, everything. University operates as a business now. Even the HPC also entirely. So anyway, the conclusions. Eventually, it was interesting. One of your research at 1 hertz very slight modification observed 3 to 5 was actually rerouting of small structures visible, especially at 10 degrees. So that was actually a very interesting effect. So we think, and that's what we need now to show numerically, that there is a sweet spot in some frequency range where the effect on this vortex will be most important, and maybe we can sustain more effect on aerodynamic performance in this case. And you see a 10 hertz dimension return. You're saying not much effect, so it shouldn't be too low or too high. It depends. It's interesting. Usual. That's your PhD, which is planning to do that one. Like do this, she's very ambitious. So she will not be distracted by chemical panel. So that's problem. Anyway, full safety simulation. All right. So this will be the project which I'll be coming back and again and again. This is the last one I'll discuss, but that's how NASA work. So I'll be talking about this. It's a like second level sophistication. There will be 2 more presentations on this. So bear with me. I'm not going to talk much about this right now. There will be 2 more presentations on this work because that's actually our like 90% of effort in the group with all different faculties, years of students involved, etc. It's a lot of work, and it's a lot of members of the team. If you look at that, it's called the Safe Low Noise Operation of Urban Air Mobility and Urban Canyons via Integration. Gas outcomes and travel. So very sophisticated title, but you need to understand what it is. It's all about future air taxis of your own.
Yeah. Please pay attention to this, and also these lectures during the week, because as professor has said, it could change our country if we implement that type of things. I am quite grateful that Professor Paso is here. I'm sad that other professors are not, because this is what we should be talking about. So please take this in mind, because it could be our future. Depends on us.
So we'll be flying non-stop from here to Manizales. Get the coffee. So for sure, that could be personal transportation. So it's all about Fifth Element. You've seen the movie, right? Remember, but then we don't going to fly like Tom Cruise, right? Tom Cruise, but this thing didn't have any kind of moving thing, like the jet, like without anything. So yeah, this thing had a lot of rotors. That's more efficient way to do this. Mother rotor system, same. So this is a kind of so our primary purpose with all this like complicated title, cast out control. It's all what happens when you fly between the heliports. So heliports will be like rooftops of your buildings, like the skyscrapers in the city, for instance, you fly from here to here, from here on through to the airport, right? And the idea is actually this area near the rooftops, where you have this atmospheric wind, right, with water layer and interacting with the whole regions, it creates a lot of turbulence in the vertiport regions, a lot of gas, turbulence, water system. So our primary purpose was to see what happens when the system is landing on the rooftop or taking off from the rooftop. Because a lot of issues with the gas interactions. And that was our primary idea. But then it actually, another thing that this is multi-rotor system, so it's what they call over-determined system. So noise could be part of the problem in optimization for the design for this thing. Because it's over-determined system. So it's part of the design metric. And so we actually will look at the predictions and control of those. Yeah, that's of course a concern. If something is flying between these buildings, the biggest issue here for public acceptance, or apart from safety, of course, don't want this dropping on you, but also noise. Noise is a big thing. You don't want to be something really like helicopter. If you will be helicopter flying, I wouldn't be here at all. And that's the thing. So we have a lot of people in the team. Again, we Boston University, Clean Tech, us, I believe, but then we have other faculty, Skigi, this guy left. Skigi is going to Skigi. And this is Georgia, this is the guys. Eventually you will need to talk to them. Because these are the guys that produce this kind of vehicles. Joby Aviation, publicly sold company, the York Stock Exchange. Now don't invest right now. Because actually, it all depends how the FAA talks about this. So when FAA talks about, okay, we're not ready for this, people not ready for that, then the stock goes down like crazy. Of course, I mean, what's going to be the market? So this is all depends on the finally getting this accepted. So in this country, if we're gonna get agreement with authorities that there will be development, deployment of the systems here in the country, then I'll be whispering you buy the stock already. Then the job will go up like crazy. In fact, there was some rumor before that they will start operating in Dubai because Dubai was ready, and then they're not ready anymore. So this thing is going on. So we'll see what happens there. But what the business plan for them was to replace helicopters at the routes which already existed. We have the infrastructure for vertiports in New York City. They fly between the downtown and the airports like LaGuardia, JFK, all this Newark. So they already exist. this infrastructure, but they're extremely loud. I mean, say because single rotor, right? When you have multi-rotor systems like this, one rotor goes bad, that's okay, you're fine, you keep going. But with a single rotor, you just rely on the rotation that will land somehow, but it's not guaranteed, depends what you have. So anyway, so this is actually very good from all perspectives to run. It's very quiet and it's safe, this thing. So they want to replace the fleet of helicopters. And that's the business plan. That's what they were showing to NASA, to FAA, to the whole public at the conferences, that this is a helicopter, do you want to fly this? And the city is like very noisy. Nobody likes to have this thing. And then you can sit in a cafe, in the coffee shop, you don't even hear it. So quiet, it's like a bird. So that's the thing. Because they already have things flying. They already have those several design built. Anyway, so for us, the purpose is actually understanding this and a single rotor with a multiple rotor response to disturbances, especially in bird force experiments, are done at Virginia Tech. So Virginia Tech doing experiments to us. We do all limitations, high, low, B fidelity. That's why I call variable multiple fidelity. The flight-based optimization is doing by this guy, but he's waiting for us to give them feedback. So if we give the feedback in terms of noise signature, then we'll proceed. Yeah, that's the future. So UAM represents the next evolution of airborne mobility. That's basically the key, right? So global market is accelerating quickly under advanced concepts. I will show later. Literally, like the zillions of companies which already exist in US and other countries which try to develop this technology. But again, they're all like in a waiting mode. I mean, if there will be public acceptance at FAA, we will accept. That's okay. Not, what's going to happen? Rapid growth rate is critical. Dynamics are predictions. Key driver of availability for electric propulsion now, because it's all eVTOLs, electric vertical takeoff and landing vehicles, right? Pushing research in batteries. Of course, everyone talks about batteries. Needs to be electric batteries, like lithium, which can sustain the flight at least for an hour or so. Unless we find invent the cold fusion. So zero emission, that's very ecological. That's from all perspective. Expected to become $1 trillion industry by 2040. That's the, some economists say that. So that's a really big industry, including taxes, carbon drones, infrastructure, And more than 200 eVTOL design concepts already in development worldwide. So it's a lot of companies who try to develop. And I'm sure Dr. Goodmanson is probably okay about it. Because it's really big thing, but of course it's a question. So there's a concept like Joby, that's the primary, and Archer, two companies, which are the main driving force in the US. There's a vertical company in the UK. There's Lilium. I heard that they're not doing well. In fact, I heard that they come back in Germany. But I don't know. There's some better, etc. I don't know. That was the rumors I heard. And check because they were like one of the biggest drivers also from Europe, along with vertical from UK. But other companies do. In fact, they do this in many developing countries. Like I went to India, I went to even not Philippines, but something else. No. Even there, they try to develop their own eVTOLs because that's something you can do. You can do in a garage. Those things. Okay, so that's something you don't need this huge facility like Boeing. Actually, one of the first concepts was developed by Airbus, because Airbus built this kind of like demonstrator for this technology. It was displayed on the conference. I remember that, and that was pretty promising at that time. But that they kind of moved this business away because they don't want to focus on this is a completely different market. So we cannot be like everywhere. So that's it. So this is like some of the concept which was NASA offering, like field prototype to bring, all these designs were produced in the original thrust by NASA about 10 years ago, where they developed this TM, technical memorandum from NASA, like the challenges for like UAM, urban air mobility. And they talk about the concept which they proposed just as benchmarks. Of course, each industry has its own, like each company, like Joby has another developed show. But it's still, it's a basic idea that depending on the size, like you can be like in a small taxi for like 4 people, or it could be like a bus carrying maybe 16 people or more. Like, it depends. So it depends on the sizing, everything depends on this. So there's many concepts which will in the consideration. And this is the Joby one. This is the Joby aircraft. How it looks like 6 rotors tilting. So they land like in a hover flight, axial hover, pretty much like a helicopter, and then it goes up, tilts. Let's go. So that's the thing. And of course, you see a lot of features which in general noise performance, economic safety. So we're just focusing on these two, noise performance. That's our objective for this particular research we're doing with NASA. So NASA, what's good about NASA? You can say it's almost altruistic, right? So they support research for us to be engaged with a company like Joby, is our partner, to be able to have the fundamental knowledge which you can create and give not just to them. Joby has just given us like geometry for benchmarking, like validation, experimental, etc. Not the latest one, some old, because they're very proprietary, very secretive. But that's something we can also show to others. And so like general public can use this information and eventually develop their own designs following the guidelines, which we create using this research. Okay, so that's the idea. Very altruistic sense. And for noise, one thing I said, but noise is a killer. Because if you look at so UAM is now replaced with the air. It's officially they try to move away for some reason from urban air mobility to advanced air mobility. So that's the official thing. We should usually put the center for AM. Okay, this Center of Excellence for AM, which is just this year started. I was putting this proposal together from the center at the university. With the idea that state Florida will give us money in the future to continue to research beyond us. Because of many, we have now Advanced Air Mobility Association in Florida, which tries to develop vertiports in this operation in big cities like Miami, Orlando, Jacksonville. Those are the primary 3, where they want to develop the system of vertiports in these operations. And they created this association to do this thing. And so we kind of like pushing this on our side. Yes. So you look at the noise sources. So I'm not sure how much of you, so now it's the first time I'm actually seriously touching on the subject of aeroacoustics. How much of you familiar with aeroacoustics as a field of study? So this is basically, let's put it, it's a far field of unsteady aerodynamics. So unsteady aerodynamics, sometimes called near field. That's what you measure on the surface of the blades, wings, all these things. When it propagates far away from this unsteady pressure on the surface, it goes into acoustics, and it's a far field, called far field. So there are methods to predict first near field, then propagate this information to the far field, using methods like green function, or the green function methods put together into classical Fox-William Hawking formulation, which follows Lighthill's analogy, acoustic and how. So there's a lot of words there, but it's all science of acoustics. There's a lot of legacy back from the 50s. When Sir James Lighthill studied this. Right. Anyways, so the parts of noise sources which we're interested in, which contribute to the overall noise signature, is first of all, for the helicopter, that's our original benchmark. For the helicopter, single rotor. Most of the noise produced is called blade thickness and loading noise. Blade thickness and loading noise is a steady loading noise. It's basically the one where it actually has the load in the blade, and the load, which is steady, usually if it's just an airfoil, produces load you will not hear it. If you just put the wing at the angle of attack, steady, you'll not hear anything. There's no noise. But when it starts rotating, you create oscillating loading. See, because it moves. So you have the first frequency tone as observer, which is located in the stationary point, and this loading is rotating now. You have something called BPF tone, blade passing frequency. So that relates to the RPM of this rotor, right? So that's the BPF tone as the primary tone for all helicopters. That's what you typically hear with single, it's a BPF tone. So that's usually the typical thing for helicopters, which you hear when it flies over. It's a BPF tone. But then, when you have multi-rotor system, it's because you have a single rotor, and you have a lot of loading, and it's very high Mach number. Usually it's like almost supersonic tips, like it's transition, right? It's transonic. So it's very high tip Mach numbers, steady loading, That produces a huge tone, and that's why helicopters just kilos, because that's a lot of noise. And then what this thing are doing, like UAM, this job aircraft, like all these eVTOLs, they try to do distributional float. It's a distributed load system. You have the multiple rotors, so this big load is distributed. You have the weight, right? You have to carry the weight. So lift should be corresponding to the weight, steady flight, right? So this lift, which is weight, distributed to many, many rotors, depending on the size and weight, right? So these rotors then in this case will be reduced loading on each one because of the distributed frame. And it will be low Mach number because you have RPMs, which is low rotational. So you have not so much Mach numbers, maybe 0.3. So much reduced. So the signature, acoustic signature is completely different. I'll show you that. The spectrum for the noise will be very different from helicopters. The primary tonal noise will be much suppressed. But there will be other things which exist. And all these things are listed here. There's zillions of them. And this is the problem. When the people were designing the helicopters, they wouldn't care about other things because they were so low compared to the tone. So tone was the primary killer. The other things, okay, they were just suppressed, subdued compared to this guy. But now it's a totally different story. All these things now show up. And that's the problem for us. We need to study them all. And this is the big challenge. So the turbulence injection, blade vortex interaction, blade aircraft interaction, engine, blade wave inversion, and then also the self noise, which the rotors produce themselves, blades. Self noise, which is the shedding from the boundary layer, the edge, and yeah, a lot of things. You see all these things come into this diagram with thickness, loading, high speed impulsive, mystic, steady, unsteady, narrowband, broadband. So typically when we talk about the noise signature, if you're like an observer sitting somewhere and you look at the Fourier spectrum, you will typically see the tone, which is called narrowband. So it's narrowband tones, which again used to be just one single BPM for the helicopter. Also for the turboprops, by the way, turboprop. If you look at the turboprop, the same thing. You typically will see this single BPM with maybe other harmonics, but that will be the primary things, turboprop engines, right? Which typically a small aircraft, but still much use. Well, general aircraft, right? Same thing. The turboprop or prop fan or any of those combinations, or just propellant. Or piston. So then narrowband not only steady, but also has atmospheric turbulence injection, turbulent wave injection, but broadband has a lot of effect from blade wave interaction, blade self noise, turbulence, injection turbulence. It all depends on the scale of turbulence. If it's a large scale structure, it becomes like tonal noise. If it's a tiny vortices, which compose the turbulence, like fine gray turbulence, and in this case, you produce the broadband, usually higher frequency broadband. So in a way, they look like this. You see, these are the tones, and this is the broadband. See, typically you have the primary tones, and then again, used to be for the helicopter. This is the single tone. This is BPM, and then the rest of these are far, far down, and that will be the only concern is this one. That's what you hear when the helicopter flies. This guy, first one. But now, as you go to this system, so all of a sudden, all of them start showing up, including this guy. In some particular low RPM operations, this guy will become higher than this guy. We have this thing now too. And that becomes a real problem because nobody ever cared about these guys at broadband. In fact, when there was research done about 5 years ago, NASA was trying to find all possible broadband prediction codes, which were in existence, a lot of them empirical or semi-empirical based on experiments. Some sort of thing, and they combine them all together. The best of the best was totally wrong. Nothing was even close to the experiments which they were run, and so they were really like shocked. And so right now we're at the stage when people are really at this broadband prediction code and huge demand. We need to come up because they become the primary tones source in many cases. That's it. That's one of the challenges. So this is actually an illustration of all these broadband noise sources. Again, in a separate presentation, I'll be talking about this guy, landing boundary layer, vortex shading. This is what produces this acoustic feedback, which I'll talk about TS2KH, LSB, all these things. This is a huge tone, but this actually becomes not just a broadband, it becomes tones as well on top of the broadband. That's even worse. But then even the turbulent boundary interaction of the wake, or the boundary separation, or the separation deep stall, or the plate vortices, all these guys see so many physical phenomena contributing to the broadband. How do you predict those things? So that's why there's a lot of, so most of this was relying on the paper from 1989 by Brooks for Marcarini. So there's a BPM model, which people use all the time for the broadband noise predictions. And that's the one which failed miserably when they compared for the solar systems. It doesn't work. So that's where they became, okay, what we should do now? And that's how I'm going to talk about this later on in a separate presentation, how we handle this stuff. Because it's a really challenge. It's a big challenge for the whole community. And this actually what the illustration is. Look at the tip Mach number. Total thickness loading broadband. So it used to be 0.8 Mach number. That's where we are. That's this PPF tone for helicopters. Right there. Nothing else. Everything else like broadband, everything else can be like way low. Now we're in the region where tip Mach number is around 0.3 and the broadband is dominant. You see, this is actually from a paper by Greenwood. He's a famous professor at State of Maryland. I forgot which university, but he's actually our co-supervisor for the grant with NASA. So the kids did famous article was about this issue with the relative components noise sources. Sound level or sound. So what we use in this case is what we call multi-fidelity approach, and that's what I'll have a separate presentation, which talks about various methods we use. From low fidelity, like atom theory, prescribed way, mid fidelity, they called by Chow does it basically the mixed panel wave vortex particle models. And then the high fidelity we use primarily open form, but also flow, Achilles. Now there's another called Lava, which came at DL3DI, which I was mentioning at first. We're not using for this one, but for this project, because I couldn't find, for a while, I couldn't find any US citizens working, well, now we have. But that's why we were restricted to open form, because everyone can use it. They cannot use, for instance, overflow, which is a NASA code, or Helios, which is an Army code, those things. But open form, everyone can use. We use this ball. So, anyway, it's on semi-RAS, hybrid LS, ES, LS. These are the biggest challenge. I mean, it's very expensive. But that's what you need to use for many cases, particularly for the broadband, because broadband relies on how well you predict dynamics in the boundary layer, and it all requires LAS because it should be wall resolved, simulation. So you resolve the entire boundary layer. And LAS, you have to have this white plus around one, takes horrendous number of grid points, which takes us to the months and months of computations, particularly even for single rotor. We used to do it for the single airfoil now on rotor, but then they talk about multi-rotors. Forget it. So that's why we moved to the mid fidelity. So we want to correlate mid fidelity well with high fidelity, and then all the multi-rotor research will be done on mid fidelity, because high fidelity is too expensive, unless we get the quantum computing. But that will be, I don't know when, because they promised it for year and year, and it's always delayed. So we don't know. And that's the thing we need to talk about. So we need to redevelop the entire code system, because CFD algorithm will be different when they run with the quantum computer. So that's it. This project we should discuss. We see a lot of things coupled together. So acoustics. So again, this is what I mentioned the legacy of the James Lighthill. Sir James Lighthill. So he was the one who developed the acoustics field. He formulated this convective wave equation for the solving the acoustics problem, which was later picked up by the guy like Professor and Hawkins, also British, who developed the methodology to solve this convective wave equation using these integrals formulated in terms of green function based on a solution in the near field. So if you have the near field, you could be the surface of the plate with an unsteady pressure on it, which you take as an input, or you have the controlled surface around, which will account for the turbulence in the near field, which is a wake till, for instance. So that will be containing more terms. Anyway, so you have to solve these equations, and that's Parasat. Ferry Parasat was the chief scientist at NASA in the 80s, something like 90s. And he developed the code, formulation rather, how to solve this equation efficiently. And so and then there was a guy who worked with him, Brentner. He developed the very efficient code called WAP. And then he left NASA and became a professor in Penn State. And now it becomes a PSU, Penn State University Walk version, which now does require authorization of NASA. So you can get this code without NASA authorization. Right now, if you want to ask just for walk original NASA code, you have to be a citizen to work on this. But if you ask Brandon, he can give you his version as a private version. And it's like open source, but only with his authorization. So you cannot do this. Actually, I secretly give it to my colleagues in Kazakhstan because we worked on this project in Kazakhstan and Nazarbayev is part Fulbright. And so they had to do some predictions. So I said, okay, don't tell anyone. But that's really the code that predict the acoustics. So they ran this and predicted the acoustics thing to me. But then I talked to Brandon, he was fine. Let's say. He went to us many times to do presentations. Anyway, so this is a very efficient population. And eventually you can look at all these noise sources we have developed. It's a dipole, monopole, and quadrupole. If you look at this, that's how they usually called. The one which developed by the like loading, it's called dipole source, by thickness displacement, it's monopole, and by the turbulence and all kinds of things, it's quadrupole. And so this is usually control surface, would be again mentioned with the surface blade. It's called impermeable surface for us from folks with importance. Or if you have the control surface outside and you just get your CFD results, get these results on the control surface and propagate far away using the formulation. This is called permeable surface. They just found some terminology, but that's it. All right, another picture of Joby aircraft in flight. So we take the rotors from them. We have 1/5 scale of the experiments and numerics, and that's what we do in our analysis. So this is like a video which shows the future, how this thing will operate and how they're going to land and everything. That's what this thing will be doing here in the university, right? Waiting on one of those rooftops and then flying to some other place. And then this is the most interesting thing. So this is the comparison, actually measured comparison for the flyover for this type of vehicle over the crazy downtown area, like in New York or anything like that. And this is the signature, acoustic signature between the general aviation like Cirrus, Beechcraft, or Cirrus was Goodmanson, Cirrus. And then some other, then helicopters like Bell, maybe Robinson, they're not. And this is Joby, look at that. That's how much noise they produce, and that's how Joby is producing, almost nothing. So literally, there's I don't have this microphone recordings, but there were helicopter flying over, and it's recorded in a coffee shop. So you see it in the downtown New York and coffee shop, and the helicopter is flying. And that's it. That's what it is. And then, so everyone jumped, with the sitting there. And then Joby flying, nobody even noticed. It's like a bird. It's literally like a bird. It's like amazing. And that's how the promises. And for this, we have to do a lot of study. Like, for instance, we need to understand how the flow behaves around these buildings when you have this wind from some particular direction. For some reason, Japanese did a lot of work on this atmospheric conditions inside the cities, like Tokyo region or some other cities. They did a lot of things. Like in our research, we did a lot of, they do Boston, because Boston University is lead. So we do measurement in Boston areas. And so they also use, so we use our simulations, but in parallel, they use what they call mesoscale models. So like Palm. So Palm is a mesoscale model developed in Germany. It's like Institute of Meteorology, Climatology, and they do this kind of when they talk now, but for them to understand what structures appear around buildings. But for them, the grid size is like 1 meter. You cannot get much from this side for our purposes. That's why we get some input from them upstream, and then we run the hyperdelta simulations, for instance, to understand what's happening really in the neighborhood of the rooftop in terms of the new pictures. And so, and that was done using OpenFOAM. So we used OpenFOAM for DES, detail simulation solution, as far as Almanis turbulence, present pressure of people solver, special different perform using second order Gauss, second order accurate current Nicholson for time, 8 order rotations. So we accumulate, so usually you accumulate time sample of 8 rotations, and then you check the acoustic, check the full field, and you get to the far field to measure the acoustics, predict. Usually that's the process. Requires a lot of things. We also use our synthetic turbulence model, synthetic gas model. So that will be another presentation. We'll talk about synthetic disturbance model. That's very important for us because we developed this model using specific momentum source. And then we can decompose this whole thing, which we predict on the far, in terms of the structures, in terms of the canonical disturbance forms, like time harmonic gas, sharp edge gas, full vortex, and turbulence with equal scales. So this is the analysis for them. And we do post-processing using what's called SPUD, spectral probe turbulent decomposition, which allows us to combine, to look at all these frequency tones which appear in SPUD analysis for the flow around the rooftop. And so each of those correspond to the specific structure. It could be one common shedding, or something on the rooftop. That's what we interest. This particular tone will be responsible for pH instability on the rooftop because you separate flow from the sharp edge of the roof, right? And so this will create this kind of disturbance, which will interact then with the rock, right? So on top of turbulence. So the turbulence, vortices, and dust like this will all have to be counted. And this is the part of the pictures which create in terms of all these structures on the rooftop, all these structures in the comparison against experiment. So it was excellent. So we get a very good validation for the results against experimental data. This analysis. We'll look at like two buildings. One of the big thing for us is what should be the flight path. So should we fly from the left if there's a wind going from this way, or into the wind, or should we land here, or should we shorter building, like shorter building which is behind in the way. So that was all the questions, and how people should operate those vehicles, right? So we measured the flight path disturbance, and that's what actually the people will be presenting in the VFS, Vertical Flight Society meeting next month, and then there will be another one next month, later next month, in our acoustic meeting. So this is the also published in Journal of Fluid Mechanics. Recently, how effective people turbulence and mechanics was similar. So you see, all this basically is LES kind of simulation, so ES, and shows all the structures. That's the thing which interact with the eVTOL vehicle when it lands or takes off, and that creates a lot of disturbance, a lot of gases. So these things may be in the wake, you can see, but it's a pretty heavy weight. It's a lot of turbulence too. So it's a question of where you should land. Okay. So we did this analysis with different routes, where this right from here, from there, etc. And then we recorded. So flight path 1, 2, or 3. Like for instance, we can hang out here, like hover and then go down, like way above the building. Or we can just go like a shorter path here and then or from this side, depending on the wind direction. And so we recorded this disturbance that it goes along flight path 1, 2, and 3, and then you can make your decision of how you're going to fly. You in each case, you see this like what you call sharp edge gust. You have to go through this region where you really get big hit. The rotor gets a big hit. It's also for the safety, right? Because you're pretty close to the surface of the ground, to the rooftop. All of a sudden, you hit this kind of big change in the velocity field, and what do? They seem to be more gradual, like flight path 3. That will be in the wind. So, and then we talked about the guys, the pilots, who actually operate this kind of vehicle. So, yeah, we'll do it in the wind, of course. In the wind, not with the wind, because they don't want to get this hit. They don't want. They prefer this. They're still hitting a lot of things, but not as bad as this guy. The sharp edge gas is really killer. So this is gradual. But then also, what about the sideways? From this side, like inside. So I don't have enough room for the picture, but I have it later. Yeah, I'll show you that instead. Anyway, so we investigated all this to give the sort of, and this, by the way, is meaningful. You see this area, the separation. Of course, when you get this kind of change from red to blue, that's what produces the same. And that's a big thing. So we compare everything against experiments in Virginia Tech. So that's Jason Alexander. Nathan McConaughey, president, with this huge wind tunnel they have in Virginia Tech. And they have this beamforming arrays. Beamforming is actually an interesting thing. They have a huge number of microphones, you see, almost periodically distributed around. And this thing is rotating, but this microphone being periodically distributed is on purpose. So beamforming technique is a very interesting technique, which allows to identify the source of noise. If you have the measurements on different microphones, you correlate all of them, you can understand where the noise is coming from. It's like inverse problem. So this is the thing which people do. If develop this method, well, not that far away in the reality, it's like a mainstream, but they measure this thing and they can see what is coming from. But they cannot explain all the phenomena. For instance, they found some taking source, which they ask us, please do some numerics. We cannot understand what's going on. It's some unusual thing. That's where numerics come. Also, doing this thing and can predict what's happening. Can try to explain physically what's happening. And then we try to compare with experiments. Black is an experiment. Blue is our predictions. Red is experiment. This is for hover. This is H-wise. When hover is just like sitting, and H-wise when you fly. But then it depends how we fly. This. So anyway, so we have everything here. Charm is a mid-fidelity code, like panel methods. Experiment, DS, impermeable, DS, permeable. And we have for the most conditions, and we found that there's also cutoff frequency we have to count for. That's what you can predict, but you cannot, depending on the grid size, etc. But the experiment for the cover was really bad. Then told us the experiment was bad. So right now, for instance, we're communicating. And Nathan Alexander came to university last week. So at university, he was actually doing this bottom line presentation of what is going on. Because for a while, they were like doing experiment and we didn't correlate well, but then they were themselves saying that the experiment was probably not good. So, it's like if the CFD guy is looking at the results comparison, he probably will tell you the experiment was wrong. If the experiment guy is looking, typically he will tell that numerics is wrong. But he's saying that the experiment is probably not right because it's very difficult. So,
Good question. Can you tell me again what is BPF?
and BPF is right the first tone here.
Okay.
This is BPF tone. Yeah, BPF tone. But this is the 4,000 meter, 4,000 RPM. So when you go back to 2,000, this tone becomes almost buried and then becomes all broadband.
Peak frequency.
Huh?
Peak frequency.
Big frequency is always BPF.
Okay.
But when you go to the low RPM, the BPF tone goes down. As I mentioned, it becomes primarily a broadband. So BPF tone gets better. This is the highest RPM value which they were asking us to do because at least you can see the tone. They were like looking for the tone because otherwise it would be like all disaster. Because if you just broadband, I mean, we basically back to square one. What do we do with this? We don't know where it's coming from. But that's why we're developing a methodology to predict. But the people experimentally cannot understand what's going on. There's a lot of things. And we just like the ones who explain the physics using our analysis, right? But they don't know. I mean, that's
One question. What is the difference between DES impermeable and
That's what I was explaining. So you either put the control surface right on the surface of the blade and you predict acoustic, or you put on the control surface surrounding the rotor. It's called impermeable. It's not coinciding with the blades. So it's just terminology they designed. Yeah, I would just say like outside control surface, but anyways. So you see, we actually were pretty good with edgewise, and they claim that edgewise is something they can trust. Because you see, there's a lot of recirculation. If you have the hover, this bounce, basically you're standing in the same position. There's no wind flowing through. So the weight goes down, bounces back, interacts again. So there's a recirculation process, which is which may happen, of course, when you land. When you land, you get this issue that the weight will bounce back and gets into the blades. So it's
It's not that in the winter how they control that because when they're landing, the recirculation happens, but also the air like dissipates towards sides. That doesn't happen in the winter because the walls are there.
and always there. So the only thing they can say, we have some bias. For instance, the results, we should look at the NASA research. They had the wind tunnel, also the same problem. They found the results are very wrong because you have this bouncing recirculating flow, right?
Because usually in CFD, like you leave like 50 diameters to every direction.
Yeah.
So that doesn't happen. But
Yeah.
how do you get that with the winter?
Well, you replicate the numerics. It's easier. You just put the ground, and we have this ground effect. I'll show you later on the separate presentation. Actually, that's the one. So you see, we put this next on the ground for the landing, and you can see how the thing bounces back. Or we can close to the edge. You see, in each case, this is actually the radiation, right? This is this kind of contours which actually indicate the acoustic propagation outside, right? And you see it's all bouncing, you have this reflection going on, but it's different if you like sit close to the edge of the building. It's actually very different physics altogether, so very interesting. And you can look at the different levels, and you see the levels could be like 70 dB difference between 69 and 78, 76. The 70 dB because of the ground effect. Because it bounces back, it creates another like reflections and everything else. So that's, of course, it's a huge thing. And by the way, I forgot to mention the most interesting thing. Remember, I was showing you go back. Well, I'll go too far, but let's see. Because it's really interesting. I forgot to mention that. If you go back to that original, yeah, this one. You see, I told you that this thing is much smaller than this guy. You know, they actually have another figure when it actually lands. This is flyover. When it lands, this thing becomes almost the same as this guy. This is the biggest trouble for them. And that's why they were so desperate to get us involved in research, because all of a sudden it becomes like a helicopter when it lands. And I was showing that's exactly all these issues with the ground effects, with the gust, with everything else. That's all because of that. So we explained to them, I mean, you have to deal with this thing. So that's what they now are working on, because this difference is all explained by physics. What's causing this thing. So
Regarding the drawing architecture, doesn't like the noise reduction happen because they really put
it's
the
distributed load.
what?
It's all about distributed load.
Yeah, but also because they're flying like an airplane.
No, but they still have rotors. I mean, they just still the rotors. They still produce noise.
But
It's a different, maybe different diagram. Directivity is different, yeah, but still becomes like a prop fan, turboprop.
yeah, but that's what happened compared to a helicopter that use them for like propulsion to keep themselves in the air. If you have like an aircraft and an airplane architecture, you can reduce the load of the propellers and reduce the noise. That's something you cannot do with.
Yeah, but that's the thing. They reduce the noise by a distributed thing. That's the biggest thing. So distribute load.
So as long as they keep like themselves in there using the propellers, the noise is gonna be similar.
Yeah, but then what happens? You have two mechanisms. Again, the loading noise is one thing, but near the when it lands, and that's why it goes up all of a sudden. There's interaction of the vortices, which bounce back and interact. So it's becomes blade vortex interaction, which is most important. And that's what produces the major input. That's why it becomes this helicopter. Well, all of a sudden, that's I don't know. You have to suppress the verticity powers. But how you do that? I don't know. You have to think about it. Is it like avoidable somehow? Some porous medium when it balances. Yeah. That's something we can talk about. Anyway, so time harmonic, that's actually a single mode of the turbulence we're investigating. Very interesting research. I'm not going to talk much about the density gust. Directing this thing. This is a small amplitude gust, 10% is the high. Yeah, this is like a single mode of turbulence. And if you look at the very interesting phenomenon, because if you look at we did a lot of studies on the gust airflow direction, classical series problem. And usually what you see is basically single tone, which corresponds to the frequency of the gust. That's what radiates the input. But in this particular case, you have the frequency of the gust, you have RPM. You have basically two frequencies interacting with each other. What do you get? And then what do you get much of the gust? So just to make it sure, because this will be explained again at a separate presentation. We primarily look at found that at the gust itself, BPF is affected slightly more on the RMS value of the BPF thrust. Thrust is affected, torque is affected slightly as well at the BPF, but nothing at the gust, nothing at the gust frequency. What's primarily gets affected is modulation torque. It's BPF plus minus gust, 2 BPF plus minus gust, 3 BPF. These side bands, which get all of a sudden going up. It's all interaction between the frequencies, which is basically non-linear interaction. That's what is very much affected. That's what we should. In the end, I'll talk about this more now. But all this is fed into the last step, which is actually looking at this flight path between buildings, how they can do this. And we're gonna that's what the Boston people do, getting all information and trying to actually optimize this flight path with minimum noise impact on these things. But then again, when you land, you actually have all the events. All right, so I was promising to show the final picture of my students. This is the car. This is like a couple of months ago. And this guy from Iran, this is the guy who suffers the most because he cannot even come back. As soon as he leaves the country, he cannot come back. That's it. And he cannot find a job either because they don't allow him. Now, this guy from China, he already found some job somewhere. So he like it. Oh no, he's still doing postdoc. Daniel, he's actually Russian, but he's American. He actually will call games. This guy is from Brazil, Michael Marquez. He's from Brazil. This guy from China, he left. This guy, Jordan, he's American. This girl, the only girl we have in our group, Daniela, she's South African. So she's like here everywhere. You know, they really like girls in terms of like engineering field. So they immediately got all kinds of awards. She's got this recently. I tell her, okay, can you have me? No, I have a meeting to like because I'm getting more there. I'm getting more. So she's got a special fellowship now, and then she's going to Purdue. That's actually one, not Purdue, Georgia Tech for PhD. And that's one of the things is that you probably like the guys, for instance, they're in trouble right now. They cannot stay. For too long because they cannot get the position. Particularly not any kind of fellowships. But she got a fellowship. I don't know. Because she's a woman engineer. So that's what it is. You have a very good luck in the US. Male engineers. I'm good at that. So Vadim is the team lead right now. He's Russian, but he's from Kazakhstan. And this is Stanley. Stanley, golden boy. So he's like complete geek. He knows everything in the world, but he's always like lost. You always have to find him somewhere because you're really like he's always in something. So like you like crash the car recently, and he's a troublemaker, but he's really like a genius. There's a lot of things. He's American. So him and Jordan both got special fellowships. Like Jordan got NASA Pathways Fellowship, so he's completely covered with the PhD, like tuition staff and everything. And Stanley got the DoD Smart Fellowship. It's a fellowship again with very high stipend, tuition. So the both are like very like in the news right now. So I don't have to worry about them. I need to worry about the gym and this guy. I don't know what to do too much because he should have graduated already. He should have defended his thesis, PhD, but he has to stay because otherwise he's out. And that's the guy I told him, like, go to Canada. Canada involves like 70% of all PhD engineering students are from India, Iran. He's Iran. He's Iran. So he's in trouble. Yeah, I don't have for some reason, Juan Philippe is not here. He should have been here, but he's gone. He probably was doing some exercise. He's always doing this thing. Maybe biking, I don't know. And Vadim was actually usually following him, but he was complaining to me because they're like buddies, like two of them go everywhere now. And he's saying, I just cannot catch up with him because he's doing like crazy stuff. And I'm not like that sporty. You have to be like professional. But Juan Philippe is like this everyone. Sport activities. So
Thank you so much.
all right, thank you.
Thank you.
Any questions?
Got a couple of questions, maybe personal, of the background picture.
Yeah. That was actually, this is an official point for all that. So people can smile.
Yes, first of all, I have a question regarding the urban air mobility topic, and maybe considering how noise was maybe a determining factor in the downfall of technologies such as supersonic jets, commercial flights.
Well, supersonic, that's the biggest thing.
Yeah,
That's why they don't fly.
exactly.
Yeah, that's it.
And considering as well that like these kind of eVTOLs wouldn't fly like alone, just one of them, but in swarms. How close do you see this technology being implemented at a large scale? And
So, yeah, we have thoughts about this. Okay. First of all, it should be fully automated.
Yeah.
I don't believe it should be piloted. Right now, the operations replace helicopter fleet, of course, pilots. And they enjoy has a pilot, of course, in that system. But in future, it should be fully automated. That's the only way I can feel a bit safer. Let's put it this way. There's many of them flying around. Noise is a big thing. Well, these are the issues. I mean, we still need to resolve them. It's not as bad as supersonic though. And what for Gulfstream was developing the business jet called Gulfstream 5, a supersonic business jet. It was back in 2005. And they invited us because they're in Savannah, Georgia, so not too far. So we were flying there. By the way, that was my only flight on a small Cessna. We had Professor Anderson, who's also a pilot, and we flew from Daytona Beach. From he's in charge of the flight research center. So he flew the small Cessna to Savannah, to the airport of Savannah of this Gulfstream, and that was the scariest flight for me because there was a lot of wind. So on the way back, we just basically landed on a single wheel like this. It was the scariest experience I ever had. Anyways, so we went there because I was giving lectures to them. And actually, later I was teaching numerical methods for Gulfstream, flying there every week. We had some very good collaboration. They still come and employ a lot of our students. But they were developing Gulfstream 5 supersonic business jet. Brilliant idea. Brilliant idea. If you search on Google Gulfstream 5, you'll find they invented the concept of the extended spike. So there's basically something like from the tip of the nose goes before it goes supersonic, before it transitions to supersonic, it extends like a long spike with like this kind of shape. What it does, it splits a huge shock wave, like sonic boom, right? It splits in multiple small amplitude. So the eventual noise signature which you measure is basically much lower. It's much lower, so it's very much subdued. You still hear, and that was enough for FAA to kill the project. It's still there, sorry. So now, of course, they developed boom with NASA. I'm not sure how it's going to fly because it's still the same problem. In fact, they try to follow Gulfstream idea, but they come to the conferences like I do all the time, talking about their progress. I understand they are ready, but I don't think FAA is ready. It's still the same problem. So that's why we don't fly supersonic, but we should. I mean, it's crazy. I mean, why don't we used to fly, right? Concorde, Tupolev 144. We had those things before, but not. So we'll still wait. Unless we fly hypersonic like this guy from the gun. Single missile delivery. Yeah. But for these guys, I mean, we need to resolve these issues for the heliports. For the flyover, they resolve it. There's no problem. Safety is a big problem. Yeah. Safety is the biggest problem for FAA. But for noise, it will be just heliport operations. That's the point.
Okay. I got another question regarding the pneumatic actuators at the root. So have you thought about using other actuators, maybe based on offsetting materials which can expand and contract?
You're the expert, you tell us, because we don't know. We just we have some guys from like Daewon Kim is our, but he's now associate dean, so it's partner. He has no time, but he's a material guy, so he has the whole lab in charge of materials, smart materials, everything. So he was debating what to do, what kind of structures, materials you want to use. So we started with this. There's other materials. You're right. I mean, there's other materials probably more expensive. So we couldn't afford to buy those at the beginning because right now we just want to look at the oscillation effects, the frequency in general, frequency effect on the whole structure. If we can prove that this thing can be efficient, then we can invest like in some more expensive thing. Of course, that's the next step. We're gonna get a grant for it. That's how you usually invest because you get the grant. You put in the grant, you need like $1 million for this thing. So that's how we do. Yeah.
I've got maybe a final question that's regarding dynamic soaring, the dynamic soaring UAV. Like you said that this type of UAV would be based on a biomimetism of
it's
of the albatross. But as far as I know, albatrosses use like different kinds of sensors to like change direction and to so how close is that implementation to reality? Because
so of course it's a closed loop control system.
Yeah.
In many ways. So sensors always involved.
Yeah.
So right now we're always debating what kind of measuring we need to do, what sort of thing we need to measure. But from velocity, it's angles.
Yeah.
angles and velocity and all these things need to be measured.
Because like all buttresses, I know they use
Yeah.
like the in their nostrils to measure like a pitof tube or something.
Smell it.
Yeah, and they also use their ears
Yeah.
to like kind of sense the wind. So
So that's great. I mean, can you come to us and look at this process?
yes,
I need definitely something
I'd
to
love to.
continue on this thing. Absolutely, yeah. We have it's setting. I'll show you that will be separate presentation. I'll show you how it's sitting right now. The whole system with all autopilot, all the computers, they're sitting in my storage room, waiting for somebody to continue because everyone is gone. I mean, that's the problem. I mean, this research. You see, the problem is that if this would be PhD research, which is actually can be very easily PhD research, but usually the kind of design things they usually consider to be master research. So they do a thesis, so they can stay for 1 year and then go. And that's it. I mean, that's why it's one after another they leave. They just barely can handle to another guy. And so this all becomes like a continuous prostration project. Because that would be a nice PhD. I mean, easy. Yeah. If you can stay for 4 years, please. I mean, that we can do a lot of things more. Because actually, it's interesting because with these ideas, which we developed, we published a bunch of AAA papers. I'm going to send. I'm going to send everything to you, then you can distribute it. So we have a bunch of AAA. We actually won journal papers, and right now we're already submitted. But it's still not finished. And particularly but there are people from startups. I remember there was a guy from MIT startup who called me for some rather big company. It's not exactly startup, they were developing. And so they basically were trying to get money from DARPA. DARPA, it's a DoD, like a cutting edge kind of agency, cutting edge research. And they were getting this proposal for them exactly on this subject. So at some point they wanted us to be part of this proposal. And then I said, yeah, of course we can work on this. And then can we talk to your student? Yeah, you can. And then as soon as they talk to my students, they say, okay, thank you, bye. So you see, I mean, in US, in general, there's a lot of unethical behavior, actually, in this sense. You see, they can get your idea and then say bye-bye very often. So you have to be careful. That's why you usually put patents. And where there are several patents on different technologies, so at least will be protected to some extent. But that happens. So, but I haven't heard about. I thought that maybe DARPA now will announce the winners, and I will not be surprised to see this project as a project for some guys. I mean, this is so far I didn't see that. So yeah, continue. That's waiting.
Thank you.
Question is, what preliminary acoustic study show be conducted to analyze the noise generated by the rotor?
By a single rotor?
Yes.
What preliminary acoustic makes the rotor? Can you repeat?
Before design.
Before design?
Say,
Can you repeat again?
what preliminary acoustic study show be conducted to analyze the noise generated by the rotor?
That's what we did, open form. Open form is a CFD based control. We predict the acoustic based on these results. It's coupled with another code, but then we also have mid-fidelity prediction.
And there are some equations based to estimate the.
It's the Navier-Stokes. Navier-Stokes. We have direct solution of Navier-Stokes equations. That's what the CFD. CFD is Navier-Stokes solvent.
Yeah.
Very close.
So
Thank you.
thank you so much, Professor. So we will do it again at 1:30 p.m. Yeah. I mean,